Okay, this lesson is close to our last one about average rates of change, but instead we're talking about instantaneous rates of change. Now, they've gone about in your textbook solving this a couple different ways. They're looking for the instantaneous rate of change when t is equal to 15, okay? And just to give you some background on the question, this is a population of some city. This is how the population is calculated. So PAT stands for the population, and T stands for time in reference to the year 2000. So essentially, if T is 15, what year are they in? Do you know?
2015.
That's right, exactly. We're talking about oh, I forgot that does that. We're talking about 2015. Okay, that's supposed to represent a 0. So they want to know exactly at 2015 what is the population changing by in that year. Okay, well, because this instantaneous rate of change, we're not using calculus for this question. We're going to talk about some methods to go about estimating it. Okay, so one way that they've gone about estimating it is they've decided to find the average, which is what we did the other day, the average rate of change between t when it's 14 and t when it's 15. So essentially, and I'm going to tell you, this is an exponential function, okay? So just to give you a quick idea of what this graph might look like, this is some function that eventually crosses at this point here and then takes off. It goes like this. So this is an exponential function. So let's say 15 is here. Well, we're going to find the average rate of change just before it, 14 to 15. And then the other thing we did is we're going to find the average rate of change between 15 and 16. Okay? So if you look at this, because we know that the way that this is an exponential function, which slope is going to be greater? The one I've drawn in blue or the one I've drawn in green?
The blue.
The blue is going to be greater. So what we're going to do is we're going to compare the two of these slopes. Okay? So we're going to find each of the slopes and then divide them by 2. So I'm going to find this slope, and then I'm going to find this slope. Okay? Maybe slope 1 and slope 2. And we're going to add them together and divide by 2, and hopefully that gives us the point in the middle between the two. Okay, and just to draw a reference to these, this will be our green, and this will be our blue. Okay, so to quickly do this, we're finding P at T, or P at 14 as our first one, which is 35,000, I believe, and then 1.05 power of 14. Is that correct? Yeah. Okay, so let's do that, and P at 15. Okay, I'm not going to write the equation out. What I'm going to do is just quickly take the calculator out, because the calculations aren't the hardest part of this right now. 1.05 to the power of 14 times 35,000. So 69297. Okay? 69297. Right? And then for 15, 1.05 to the power of 15 times 35,000. 72762. 72762. Okay, so right there are our two y coordinates, right? And remember, when calculating slope, it's change in y over change in x. Okay, so we'll call this. This will be our y. This will be our x2 and y2, and this will be. Thank you. And this will be x1 and y1. Sometimes I get ahead of myself.
Yeah.
Is that good?
Yeah.
Okay. So we take 72,762 and subtract 69,297 divided by. I didn't want that right. Divided by 15. Good. Minus 14. Well, that's obviously going to be over 1. So whatever it is on top is going to be our slope, right? So we're going to subtract those two numbers, and I think I have one of them already in there. Perfect. Well, because we round it, we'll just stick with the numbers we had. So 72762 subtract 69297. 3465. What they got there?
Yeah.
Yeah. 3. Is it?
6.4 though.
Oh,
That's
because we
of
rounded.
rounding, yeah.
Because we're rounded. So 3, 4, 6, 5. That's fine. 3, 4, 6, 5. So that is essentially, we'll zoom out a little. That is the slope of our green. Highlighter we want in green. So that's the slope of the green part. Now we're going to find the slope of the red part. Well, luckily, we already have the slope at 15. We already know what that coordinate's going to be. So we only really have to solve for 16 right now, that coordinate, exactly. Not the slope at 15, sorry. We already have the coordinate. So let's find P. Oh, gosh. Sometimes my colors get mixed up. P at 16. Okay, well, P at 16, same idea, 1.05 power of 16 times 3,500,000, sorry, 76400. 76400. Okay, exact same idea. In this one, we'll just kind of change the values. This will be our x1, y1. This will be x2, y2. Okay. So in this one, you know what? I'll do it in blue, just so you have contrast. 76400 subtract 72762. Is this making sense?
Yeah.
Over what is it going to be? 16. Well, we'll write it. 16 subtract 15 is going to be what?
1.
Well, yeah, it's going to be all over 1. So we just have to subtract these two values. 76400. 72762. 3638. Is that pretty much what they got?
Yeah, 3639, but yeah.
3638. Thank you. Okay, so those are our slopes. That was the slope of our first one in blue, so leading up to 15 and just after 15. So we have the slopes of the two of them now. What we're going to do is take these two slopes, add them together, and divide by 2 to essentially find the average between them, or essentially the point between them. And why the reason we find the point between them is because the point between them is 15 right here. So that's why we're going to add them together and try to divide by 2 to find out that point. So 3, 4, 6, 5 plus 3, 6, 3, 8 divided by 2. So the estimated instantaneous rate of change, 3, 4, 6, 5 plus 3, 6, 3, 8 divide 2. 3, 5, 5, 1.5. 3, 5, 5, 1.5. And usually they estimate this to be about 3,500 and, round it down. Because we didn't do our rounding before, it's probably 3,550. Yeah, it looks like that's what they got per year. Okay, so that's essentially how much the population is increasing per year when we solve it through this method. Another way you could have solved this, let's see, do we want to go into it? That took 8 minutes. We'll make a second one about estimating, okay?